Hello, everyone. My name is Philippe, and I'll be one of your speakers this afternoon. I currently work as a solutions architect at Astronomer. Astronomer is a company that develops commercial products on top of Apache Airflow, a project to which we're one of the main contributors. In that sense, we have a business model very similar to what Starburst is doing with Trino. Previously, I worked in data analysis and data engineering capacities in the financial sector with large and small institutions. I am a big Python fan, a big Airflow fan, and a big Trino fan. And essentially, I just generated this image using Stable Diffusion to fit the Pokemon team here. Nice. So here's our agenda today for this presentation. First off, we'll start by taking a look at the traditional data architecture and reimagine it using as a federated data layer. Second, we'll pose the thesis, which is that batch fits in this new model, and that Trino is a great tool for this as well. Then we'll introduce Apache Airflow as an orchestrator for Trino queries, and finally, we'll look at how to use Airflow and Trino features to structure Trino workloads. So throughout this presentation, we'll work on the data infrastructure for a fictional trading or investment management firm. This is really simplified. In fact, the folks from Goldman here today are probably rolling their eyes right now, but hopefully this should be enough of a bone to play with. So let's take a look at the main components. On the left side, we have our data producers. Those are the various subpersonal systems or processes that create data that the company uses in the course of its business. Sorry, my laptop's not working here. Essentially, we've got CRM on top, which could be Salesforce or Dynamic, which the company uses to manage its customer relationships. In the second box, we have essentially the data infrastructure for the market data team, and they're responsible essentially for ingesting data files that are sourced from various vendors. In the bottom, we have our operational data systems, which essentially our clients use to manage their trading accounts day to day. These folks are using a Postgres database and the web app in front of it, essentially. In the center, we have our central data team, essentially running a centralized data warehouse such as Snowflake. And they're responsible for running the pipelines that ingest the data into this warehouse. We've got data governance and infrastructure teams essentially maintaining this. On the right side, we have our data consumers, which are various data teams that use this data in their day-to-day. So we're talking, for instance, risk, compliance, analytics teams, and they produce reports, send emails to regulators and different decision makers throughout the organization. So this is how most data teams operate today, and everyone's familiar with this model. However, in my opinion, there are multiple issues with this approach. The main theme here is that the central data team has to be responsible for building the integrations between data producers and the central data platform. This is problematic for two reasons. First off, this does nothing to disseminate knowledge and increase data literacy throughout the organization. The data team gets overloaded with requests and fallbacks to a transactional service model in order to manage their workloads. Second up, the data team views the producer's data from an external point of view and is further removed from the business context that they're operating with. Finally, the integrations they build are exposed to unpredictable changes in the source database, and while attempting to keep up with said changes, the data team can easily become a bottleneck for the business. So let's introduce Trino in this data stack. So Trino allows you to run a federated data queries as close as possible to the data source system. So essentially, the labor-intensive process of moving data into stages before ingesting it into a central warehouse is now mostly abstracted away. This doesn't mean that data movement is no longer necessary, but it does mean that the need for it shifts from being an availability concern to a performance and scalability concern. Benefits to your organization with this approach is that without investing in additional resources, your data professionals are able to partner more closely with their stakeholders, and this increases data literacy and data availability throughout your organization. So let's take a look at how this looks. Essentially, we're replacing the warehouse with a Trino semantic layer, and instead of moving data into Trino, Trino performs queries against source systems. The data engineers are working more closely with their stakeholders, and we have a federated governance team in place that basically ensures that standards are followed throughout the organization. As an added bonus, you can run your Trino cluster anywhere. In the case for my demo cluster, it's located on the mod SDKS cluster running on Spot instances, and this costs about $12 a day. It provides 32 vCPUs and 256 gigabytes of memory, which for all practical purposes, in my experience, is sufficient for the workloads of probably 99% of organizations, to be honest. And it's way overkill for the use cases with which we'll be toying with here. Here's the data model we'll be working with our data contained in unconnected systems. So essentially, we rely on a mapping table to look up IDs across systems. We have customer data in Salesforce, to which we connect directly using the Trino connector. We have trading data in the trading ops database, which is the operational database used by our trading platform, and that's running Postgres. We have market data in the data lake on S3, essentially. We use Hive as our meta store and Parquet as our FOSS format. And we have a mapping database which maps the database IDs for records across entities that are related throughout this model, like I said. And finally, we have an analytics data warehouse, which is essentially used as a staging location for results for analysis and to stage data for caching purposes. So for analytics use case, ideas from the data mesh model are gaining a lot of traction. But they're also applicable to batch workflows. And while proponents of the data mesh approach insist that it's an organizational pattern first and foremost, processes require tools, and I'd argue that Trino is one of the most suitable platforms in which to implement a data mesh. That's because it's a great fit to process data in this kind of federated model, which we find pretty much everywhere, although it's generally not exposed. On top of that, it's fast, running queries in memory, and much more reliable thanks to new fault-tolerant features that were introduced earlier this year. It has lots of connectors built in and a flexible SPI that allows your users to roll their own connectors as long as data can be represented in tabular format. If built-in SQL functions are not good enough, it's possible to implement transformations using user-defined functions. Basically, this all allows you to run transformations that add value without having to explicitly move data to intermediate systems. Data movement can be as simple as create table, as select, or insert into another system. However, designing heavy batch workloads to run on Trino was challenging and required teams with specific skill sets. This means a rare breed of people who are both able to understand data analysis and apply an engineering mindset to the problem. Batch workloads often have complex interdependencies and sequencing requirements. They're also often mission-critical processes, and their failure needs to be logged, alerted, and handled. In order to help with this, we use an orchestrator such as Apache Airflow. So what is Airflow? Apache Airflow is an open source platform for developing, scheduling, and monitoring batch-oriented workflows. This is taken from the website. It comes from the Airbnb, where it was developed by Max Beauchemin to orchestrate their big data queries on Hive. It was open sourced in 2015 under the Apache Foundation umbrella and became a top-level project thereafter. In contrast with point-and-click tools, it's a platform to programmatically define, schedule, and monitor workflows. It essentially introduced the concept of defining orchestrated workflows as Python code. It has a very strong community and is used by organizations of all sizes around the world. In order to define workflows on Airflow, we define what we call a DAG, which stands for Directed Acyclic Graph. It's essentially a graph of interdependent tasks. In Airflow, the payload for these tasks is defined by an operator. Operators use hooks, which are interfaces to connections under the hood. They're both distributed in provider packages. Airflow has hundreds of built-in operators and hooks in dozens of provider packages, including, of course, one for Trino. This exposé wouldn't be complete without some screenshots, so here's the DAG overview interface. As it said, it gives an overview of the DAGs running in your system and their state. Here's the graph view of a DAG. This basically shows the dependency graph between related tasks and allows you to select them to drill down further if you need to. And here are a few actions that you can take if you drill down into a specific task. This is important, for instance, for monitoring purposes and failure handling specifically. Let's talk about how to structure Trino workloads on Airflow and how Trino and Airflow features can work hand in hand to successfully process data at scale. We'll start by looking at the basic Trino DAG and introduce some added complexity through checkpointing and dynamic task mapping. Then we'll talk about Trino's recently introduced fault-tolerant execution mode, and finally we'll talk about one of the newest Airflow features, data-aware scheduling, and what it brings to the table. So the first approach is what I call the brute force approach. It's essentially the simple, naive approach that pretty much anyone can implement really quickly. So this basically consists of sequencing long, expensive queries and handling requires with the default Airflow mechanism. This is what this DAG looks. This is what this DAG looks like in code. Sorry, I forgot to set something. For the next few slides, we're going to structure fictional workflows at our brokerage firm. At the end of the trading day, our brokerage firm needs to perform a few operations. It needs to process deposits and withdrawals for its customers. It needs to net the trades it performed throughout the trading day. It needs to compute account balances, which are not only an important metric in and of itself, but also used by other processes downstream. And it needs to calculate the margin requirements for its accounts and verify if they're breached. It runs all these operations in batch queries on Trino, orchestrated via Airflow, and wants to understand how to structure these workloads. Like I said, the basic DAG, the brute force approach, essentially. It's the simple, naive approach to building a workflow on Airflow. And this is what this DAG looks like in code, and I've highlighted the important parts. At the top, we have a default argument passed to all tasks in the DAG. In this case, we set the retries parameters to 3 with a retry delay of 15 minutes. Under that, we have the DAG definition itself as a context manager with a few parameters. There's the DAG ID, which is a unique identifier, the schedule interval, and the default arguments defined earlier. Then we have our task definitions. On this slide, I'm only showing one for space in the middle column, but there can be as many as you like. The task shown is using Trino operator, defines the connections it uses to connect to the Trino cluster explicitly, and passes a reference to a SQL query in a file as the payload. Under that, we have the task dependencies definition, which is accomplished using the bit shift operator. And on the right, the actual payload. So the problem with this approach for long, expensive batch jobs is that if the Trino query fails for some reason, such as running out of memory, the retry mechanism isn't granular at all, and the whole query needs to be relaunched from scratch. If the query takes multiple hours, which is not the case for this one, but it could be, this can lead to a breach of SLA easily. In order to address issues with the previous approach, we can introduce sharding in our DAGs. This is a technique which consists of splitting a long-running, expensive query into logical parts. These logical parts can be executed independently and output intermediate data sets which downstream tasks use to continue processing until the end result is achieved. Airflow is a great framework for this, as it allows DAG authors to easily sequence subqueries and monitor the execution of full workflow in one place. So the pros for this approach, essentially less work to be retried in case of query failure, improves landing time when things don't go exactly as planned. And the cons for this approach is that it requires manual optimization because the query planner does not have the full picture of the complete unit of work, and the query wrapper needs to have a better understanding of the query planner in order to find suitable parts to extract and run independently. It can create very complex workflows. So let's edit our DAG from a previous example in order to take advantage of this. In this case, we'll simply split the work according to account number prefixes. And this could be a good split, essentially, if the splits are evenly distributed and the source system has matching partitions, but that's a big assumption and it should be checked in practice. We can accomplish this essentially by creating a loop, or creating our tasks in a loop, essentially. And afterwards, we'll parameterize the task ID and pass the group's identifier as parameters to our SQL queries before submitting them for execution. This is what the templated query could look like in this case. Notice the templated predicate highlighted, which maps to the params passed when the task was instantiated. Of course, the usual caveats when templating SQL queries apply. Be careful about sanitizing inputs, and et cetera, et cetera. Also, another thing to note is that you need to be aware of which connector Trino uses to connect to your data. Even if you're using this technique with some connectors, or if your data is not laid out as expected, this could actually do more harm than good. In our previous example, we showed that we could split a query according to predefined buckets, but what if you wanted to split your work depending on information that you can only obtain at runtime instead? This is where dynamic task mapping comes into play. Dynamic task mapping introduces the ability for users to generate new tasks at runtime based on data, rather than having to know ahead of time how many tasks would be needed. For instance, let's assume that we want to process amounts, account balances, and margin. but split the work according to which counterparty bank or which counterparty brokerage we traded with. Additionally, let's assume that our counterparty relationships change relatively frequently, which makes keeping a static list impractical. So yeah, let's structure a DAG that handles this case. Here's a sample from the DAG code that allows us to do this. The important parts here are the introduction of the partial and expand methods. So we use partial to define arguments that are fixed for all instances of a map task, and we use expand to define the dynamic portion of a map task. In this case, we pass the results of a task called getBanks, which performs a query on Trino against the bank's dimensional table in our model. And we use the results as map parameters, which are subsequently used in the second task. The second task runs our query, which computes cash balances by accounts, but this time filtered by counterparty bank IDs instead of arbitrary buckets. In the subsequent steps, we would use these results for further aggregated processing. This generates a DAG that isn't structurally much more complex than the base case that we looked at first, which is what we want as much as possible. So at this point, I've been talking a lot about how to track workloads outside of Trino to reduce the consequences of query failure, but for a few months now, Trino has had much more robust failure handling capabilities, which we can take advantage of. So Trino now has two retry policies. Those are query and task. Query-based task retries are interesting, but not really useful when an orchestrator is already in play, as whole query retries can already be handled at the Airflow task level. In fact, I'd argue that this is the preferred way to do it, as Airflow has more flexible failure handling mechanism capabilities, such as alerts and callbacks, and et cetera, et cetera. However, the task retry policy is a game changer because it allows Trino to retry an individual Trino task within an execution plan and continue as if nothing had happened. To understand how this works at a high level, let's take a look at the plan for a Trino query. This is a generic select query across multiple tables with joins and aggregations. Each step in the white boxes is a task. Previously, the output for these tasks would be kept solely in memory, which has two major implications. If a node fails while running a query, the work it performed is lost and the query would fail because that's unrecoverable. If a node ran out of memory while running a task, the query would fail as well. This required acrobatics around query scheduling. With task retry policy, Trino will pull task output to durable storage, which allows workers to retry failed tasks in the middle of the execution plan. This requires configuring a new component called an exchange manager that's responsible for storing and managing spooled data for fault-tolerant execution. So basically, this introduces automatic granular checkpointing to Trino. The caveat is that sometimes the cost of task-level checkpointing is not worth the overhead in cases where recovering from failure is less expensive than spooling. But nevertheless, I'd recommend enabling it in your query if your query completes on average in like 10 minutes or more. It's worth it. This makes Trino queries much more resilient to failure and viable for long, expensive batch jobs, and I would argue makes sharding much less relevant. Finally, let's talk about one of Airflow's newest features, which is data-aware scheduling. Data-aware scheduling introduces the concept of data sets in Airflow. In the Airflow context, a data set is a stand-in for a logical grouping of data that shares a common identity. Data sets are updated by producer tasks, and data sets updates can contribute to scheduling consumer tasks. In a Trino setting, this allows a team to launch a batch job that consumes a data set produced by another team based on interdependent transformations in a decoupled yet explicit way. So let's take a look at how our brokerage is using this feature to decouple the work of its accounts and risk team, which are now producing and consuming data products. This is the code required to make use of this feature. So it's really simple. On the left, we have tasks that produce data sets and define outlets. In this case, the accounts team is producing an accounts balance data set. On the right, we have a DAG definition that bases its scheduling decisions on data dependencies. The risk team's batch jobs have an explicit direct dependency on the account balance data set being updated. This means that its transformations won't accidentally trigger and run with stale data. This is really simple, but also really powerful. More concretely, here's a view of how the Airflow scheduler takes these dependencies into account instead of a fixed schedule for its DAG scheduling decisions. So yeah, essentially, as you can see here, instead of having a fixed schedule as a trigger condition for this DAG, we have dependencies on data sets produced by other tasks. Note that the task can produce multiple data sets, and conversely, a DAG can depend on multiple data sets as well. This means that the DAG will only trigger if all data set it depends on have been updated at least once since its last run. We can see data dependencies very explicitly in the datasets page, which gives a list of data sets defined on an Airflow instance, as well as a dependency graph between the producing tasks and consuming DAGs. So the takeaways, essentially, the brute force method for running Trino is viable, but task-based fault tolerance should be enabled on your cluster. In fact, I would recommend enabling task-based fault tolerance by default if your tasks run for over 15 minutes on average. Trino task-based fault tolerance reduces the need for shards in your code. Dynamic task mapping is a great way to structure workflows if you need to adapt their structure at runtime. And finally, you can produce data sets so that other Airflow users within your org can use your data products efficiently with data-aware scheduling, as long as they're sharing the same Airflow instance. Thank you.
Do we have any questions?
I just caught the tail end of your talk, but I found it very interesting, like this concept of data sets. But you said only if your Airflow, if the tasks are in the same instance.
Yeah.
What if they're not?
In this case, essentially, you can't make use of this feature, but there's multiple techniques that you can use to basically trigger a DAG from another DAG. The easiest way would probably be to just make an HTTP call to the Airflow REST API and trigger a DAG that way. Thank you.